This one. This one. Is that the right one?
This one. Okay. Okay. I hope they. I presume it's all microphone working. Yeah. I think it's only one.
It's the wrong one.
No, it's right. It's correct.
It's right.
I think you open two of them. I think it's been open. But it's correct.
This one. Well, this one's the one that's sharing for the recording. This one.
Thank you. Okay. Thank you for opportunity to speak with some kind of results, which been actually the summary of the interesting work on again return to Relaxor. So just look a little bit back on what else Relaxor could do. So this talk will be about the optical properties. So a little bit switch on and kind of how basically how we can control dynamic and optical properties at the same time. So this, yeah, this is a summary here. It's the product of the collaboration of the multiple groups. So that's what I try to highlight what's been happening recently in that area. So first of all, let's be very brief and do some trivia. So we know that energetically favorable to form ferroelectric domain in order to clearly to get high ferroelectricity. So clearly the domain can provide all multiple functionality in the without domains we hardly we can see the large piezoelectric response. And unfortunately, or not fortunately, or unavoidably, the piezoelectric coefficient in domain engineering material is coming from domain walls. However, at the same time, the ultra high optical activity, which really wants to be like kind of 100 picometer per volt, or preferably even higher. However, in many cases, because of high piezoelectricity, the domains are actually preventing material to be transparent, so it makes them opaque and creating light scattering. So essentially, that is the dilemma which we look in this, and many groups try to look in this, and they try to solve this problem different ways. So the material simultaneously very rarely produce high piezoelectricity and high optical properties. Exactly why? Just because of, like I mentioned before, because of light scattering. Multiple attempts to been shown the how to organize domain using the AC polling or using the various actually multiple methods in kind of like kill domains in a material, try to make the material transparent, and some of them successful, some of them less successful, but like in work which shown here in the middle. So the works that try to make the material transparent by totally eliminating 71-degree domains from scattering. So making the material actually essentially the more or less homogeneous from optical point of view in that particular direction, not scattering. So what we try to do in this set of measurements, we try to find how to do the piezoelectric response and the optical property at the same time. So I know maybe this is very not favorable functionality, but this is what we try to do, and this is what I show you next. It's why actually is this of interest, why the actually way how to do this will be some interest in doing. So when you look at a multiple electro-optical material, you can see that in material with a high piezoelectric activity, clearly the will be with the highest optical activity. So this is clearly is a very high opportunity for transparent ferroelectric for multiple application for high speed, and this is what I mentioned. So again, the question remains how to do this, how to combine two of that properties together. So one work which we will look on our colleague Laurent Belais, who actually showed, and his group shows that definitely indeed you can see that the piezoelectric can increase in optical properties is clearly will be linked together with the increase of the electro-optical coefficient. So a couple of the calculations been shown that it's a D3 coefficient and R33 and will be close to the maximal and close to phase transition. So if I go back again, so that was actually quite very interesting. So the highest strain and highest electro-optical activity linked to each other. So that's what this actually give us some stimulation for all this experiment was what I show you next in a couple next slides. So that the just background for this work was Laurent did in this work before, trying to show. So our experiment or our demonstration, if it's kind of use the method which been noticed for absolutely different applications. For application is to looking for acoustic devices, so how looking to stable acoustic devices, whereas the normally phase transition actually completely killing the stability and making your acoustic device completely non-linear. So that, but what's most interesting is that the same phenomena of the switching the from phase transformations shows us that actually the optically it can be quite interesting outlook. So what we look at that phenomena, what we call the kind of optical tuning or transmissivity tuning from definitely scattering phase to totally from opaque to transparent phase. On example of a PMN PT based system, in this particular PMN PT crystal, using the stress and electric field. So that's what shows the next data. I can show you that it's definitely possible. So it's just a couple of slides which really probably not needed. So what's clearly that the phase boundary between the rhombohedral and the rhombic phase can be moved not only by composition and light, but field and stress. So essentially, if you try to find material, posing the material exactly on a close to the composition close to the perphetropic phase boundary, so you can switch very easy. So that's like today, we talked today that it's a flat energy landscape, allow you to do almost energetically cheap, if you wish to say. So that's the whole point of that exercise. So phase transition, a near perphetropic boundary can do it, can be done very easy. So what's happened if you take the crystal and cut the crystal some very special way? So to make the PN PMMPT in 011 cut and apply stresses, what's happening actually is what I mentioned before. The material undergoes the phase transition, stress as well as the field transition, where the all available variant actually collapse from rhombohedral state to rhombic state, and eventually making polydomain state with the domain typically range along the 001 and 001 or 011 plane, actually collapse into the 011 plane, making the essentially crystal, kind of correctly speaking, monodomains. So that, remember, this exactly was the goal to get the optical property that making the no domain wall, no heterogeneity of the system. So that was actually quite interesting phenomena, which again, been definitely very bad for acoustic material, which we're thinking that maybe it can be done something else. So so again, a lot of work been done on this in this area with several groups showing that if you take the material, actually what's quite interesting, so that flipping from rhombohedral to rhombic with definitely with some very complexity of the phases, can be done actually many times. It's actually it's been shown that it's going to be tens and million times it can be done without destruction of the crystal. So it's quite interesting. This is kind of, again, very technologically interesting phenomena. So in order to see what's happened inside, our colleagues construct special system to do the in situ and operanda works. We do under compression and stress. So everything can be done in situ, and at the same time measures the structure and do the X-ray experiment on this crystal. So that actually also help us to observe quite interesting phenomena. So essentially, that's exactly what we are looking for. We're looking for the way how to prove that you have a monodomain back and forward to polydomain state can be done reversibly. It's exactly what it's shown in this picture. So you can see how the essentially the peaks splitting peaks shows that under stress. The no field here, how the peaks actually collapsing under stress, indicating clearly that you have a phase transition and one kind of survived to rhombohedral phase is going to monoclinic with increasing stress. So essentially, we're demonstrating with the X-ray as a function of stress. We're also demonstrating the same thing with the TEM. So the domain is actually disappearing. So basically, like it's shown on a corner photograph. So with the stress in a TM picture. So essentially, this nanodomain which disappear when the force apply along the 1,0,0 direction. So that's kind of whole scale proves that it's what's happening. There are another techniques also been involved. So the techniques to show that you can use what kind of and it's like the equivalent of the Kikuchi line. So GMS technique is different. It's a diffusion multiple scattering, which actually indication of the two phases collapsing in one. So essentially, what's shown here is that one single crossing and with the two several lines indicating the presence of the several phases. In the low stress in zero field, you can see several lines indicating that particular multi-phase coexistence itself. Clearly, to look at the model of what's actually happening with the optical signal, it's been employed just regularly, very straightforward kind of dB law, like to show that scattering by on a domain wall. So that, and interesting enough, so this is what you see on a transmission signal. You can see that essentially the high stress and low stress fit in quite well with this equation, and shows a change in transmissivity about from 1 to 70%. So material became totally transparent at high stresses when it undergoes a phase transition itself. So it's another technique, and again, so it's a bunch of techniques being employed to show the diffuse scattering, to show that indeed the domain, polydomain, and monodomain state are definitely reversibly switched. This particular experiment is exclusively no stress, just with electric field. So physically speaking, from all directions, we come to the same conclusion that you can switch material reversibly with field and strain, or with a combination of both of them. So, and of course, interesting to see what's actually the optical experiment could look like, so that you can see what the stressing and unstressing and implying electric field. At the same time, you can see the material actually the change in the transmissivity at the same time, and it's quite repeatable phenomena which can be done many times, and when it's linked together with the like shows in the plot here with the total strain, so that you can see that strain and the phase transformation strain totally coincide with the transformation on a phase transformation, which shown in transmissivity itself. So clearly the application required to look on the dynamics of this of this phenomena. So we try to look, and we continue to look on the time resolved measurements. So where essentially the electrically driven phase transition will change the transmissivity, like it's shown in a plot here, with the light transmission driven through the very slow time variable manner with several hertz, but the switching occurs on an absolutely different scale. So this is really very interesting phenomenon. So essentially the whole propagation of the whole like I would say area of the phase through material definitely is not equal to the in the time scale with the electric field. So that's very probable link to the elastic wave, which limit of the speed probably of this phenomena itself. And you can see the several regions of this phenomena which really can be associated with different crystal structure. This is what's been shown on the slide on the back. So, and what's most interesting, so that, like I mentioned before, that the transmissivity change up to 70% can be also accompanied with a very large strain. So that's what's shown here. When you just linear strain below transition and high strain above transition, allow us to get kind of effective coefficient like higher than 10,000 picometers per volt, which actually is quite high again when you try to look in that particular domain general crystal, that can be done reversibly and optically also in the same time. So that is kind of bring me to conclusion of this work. So I think I hope I kind of demonstrated our assumption, and I hope I kind of showed you that in our crystals, which can be chosen right way, the switching between kind of optically transparent and optically opaque mode can be done very reversibly with the change large piezoelectricity. And a lot of questions still remain. So how to fight with the hysteresis? So what's the how actually make the switch faster? So what actually happened inside? How to make this phenomena actually more attractive if you really want to do it? The optical devices based on that phenomena. So with that, I probably stop and take questions.
So I'm trying to understand, so you mentioned the work in art, theoretical work, and this question, you see teachings in the talk, but I do not hear it either. That's kind of an intrinsic change of the moral, the moral moments. But I do not hear is you are moving on the force.
Yes, that's correct. Yes.
So, have you seen anything that actually interact connect with your data in Atlas or
No, that actually link together the demand for finding the material with the high piezoelectric activity and very high electro-optical activity. So this kind of all theoretical work is it give us justification that to search in the right direction as much as closer to the phase transformation mode. So effect which I talk about, that essentially domain or extrinsic domain one, it's will just basically side effect on the optical side, which preclude us to see that phenomenon. So, but again, that was just stimulation of that work.
So usually imagine you use color light or even phosphor light, you use much more feature in terms of optical and probably in the second level. So what do you have you thought about that?
No, absolutely, yes. That's kind of planning of this experiment to do in in a much faster mode to do polarized light microscopy. So yes, actually, we did the polarized study, and as we did see the huge difference. This is no question about it, because you have a domains which really are participating in a electro-optical capsule. Yes, answer yes, it's in the plan. Yeah, you're absolutely correct.
If you like to pancake from mine here, the kind of conceptual question, you want to get simultaneous high electricity at something. So you have to be monodomain at DC mode to be transferred. How about the theoretical property of a small signal theoretical property at that transfer state of a D standard is not high?
Your question, if I truly understand your question, you're asking what actually is a small signal property?
Yes, by DC voltage. The DC at that DC voltage
Yes.
is supposed to be high by the voltage.
That's actually interesting question, because the voltage was required to switching from one phase to another phase, it's actually not as high. It's only a couple of kV per centimeter. So that is not dramatic voltage. So that's, it's you or me? No, I think it's you. Yeah. So I think it's that was a kind of compromise, that particular phenomena can be done at relatively low voltage. So, and it could be reversibly low. It means the kV per centimeter. So it's relative, because normally, typically, the high voltage is definitely something comparable to the corrosive field of this PMNPT, which much more than 3, or this particular even more than 7K. So again, this is much lower than switching 180-degree switching. So that's why I consider this as a low voltage. This for you. This for you.
Test. Hello, can you hear me? No.
Are there two mics?
This one? Can you hear me now? Okay, great.